Hey everybody, we move on to our next lecture in Unit 2, Exploring Two-Variable Data, in which we talk about this thing called Pearson's correlation coefficient. So, as we saw in our last lecture, describing the strength of an association could be kind of difficult between two quantitative variables, and what we found was we needed a numerical way to do that, and that's what we're going to tackle today. Our question really becomes, how does a correlation coefficient R describe bivariate data? So this is one of the big key statistics that we will look at in this course. Let's get into it. Now, if we were looking at these two scatter plots, my question to you is, which one seems to be stronger? Most students will take a look at this and say, well, to me, it kind of looks like these dots are all closer together, so that's going to mean it's a stronger association. But take a close look at our scale, and you notice that these two distributions are actually identical. The scale has just been changed. In the one on the left, all we've done is we've zoomed into the same exact scatter plot as the one that's on the right. So your eyes can be fooled, and you got to be really, really careful about this. And what this is going to tell you is that you are going to need some kind of numerical way to describe strength in association. We need some way to get around this idea of something strong, very strong, moderately strong. Is it only weak? Is it moderately weak? Or is there no association at all? And the way we do that is by calculating Pearson's correlation coefficient. It's also called Pearson's product moment coefficient. Okay, but it's R, the correlation coefficient R. And there's a lot of different ways that we can talk about association between quantitative variables, but this is the one we are going to use most. Okay, Pearson's correlation coefficient, here's our formula. Looks pretty gnarly, looks pretty gross, right? But the good thing is you're never going to really calculate this by hand. We're going to allow online calculators and our graphing calculators to do this for us. But I want you to see what goes into it. First of all, we see that there are two variables indicating that it is quantitative bivariate data that we are examining with the statistic. Hopefully we remember seeing this from our standard deviation calculation, where we have the sigma, that's the summation, and then we're dividing everything by n minus 1, or our sample size minus 1, right? The idea here is that we are looking at taking the sum and dividing by our total number, which means we are taking the average, okay? But what are we taking the average of? Well, it's x sub I minus x bar divided by s sub x. We should remember this is our mean, x bar. This is a standard deviation of x, and then x sub I just says each individual. So what does that mean when we are taking each individual minus the mean divided by standard deviation? You should know what this is. You should hopefully recognize it. Maybe you don't recognize it because the notation is different, but it's still the same idea. What happens when we take an individual observation, we subtract from it the mean, and then we divide by the standard deviation? What is it? That's a z-score. As I mentioned before about z-scores, how this one formula can be is going to derive several different statistics that we are going to use in several different key components all throughout our course. They don't go away. Z-scores are super important. So not only are we looking at the z-score of the x, but we're also looking at the z-score of the y variable, and we are multiplying them. So it's the average of the product of two z-scores. It's not actually two z-scores, but it's a z-score for x and y, and we are multiplying all of them. So it's the average of the product of your z-scores for every individual. Okay, the x z-score and the y z-score. Now that still isn't really super clear mathematically what that's telling us. So let's try and just define this in English terms. In English, R, the correlation coefficient, measures the strength and direction of a linear relationship between two quantitative variables. Now, super important about this is that this only works for linear relationships. And you'll see what this means when you go through your examples or in your practice assignment for this lecture. You will end up seeing where we have things that aren't quite linear, but we can actually see that there is a very strong relationship. But the correlation coefficient R won't indicate that it is. So this is super important. You're only going to use correlation. R only works if you can see that your scatter plot shows a linear relationship. Okay? So in this, since we have a somewhat linear relationship here, we could calculate the correlation coefficient, and it's going to make sense. If we had something where we had more of like a parabolic or a quadratic kind of relationship, that might be really strong, but the correlation coefficient is not going to make any sense at all for it. Okay? Now, let's continue to work. How are outliers going to affect R? Is it going to be a resistant measure like median and IQR, or is it going to be heavily influenced? So stop to think about it for just a moment. If we look closely at our formula, we understand that we are taking the average. Not only are we taking the average, but the mean of two different values is going to be included in that calculation for R, and the standard deviation for two different values is going to be influenced in the calculation for R. Now, mean and standard deviation, if you remember that those are not resistant measurements, then it should stand to reason that R is not going to be a resistant measure at all, which means outliers are going to heavily influence R. So, no, we would say that R is not going to be resistant to outliers. Mean and standard deviation go into this calculation. Of R. Outliers will heavily influence correlation. Now, one thing that we can do is actually see how to calculate this, not by hand. We don't want to calculate it by hand. It's way too time consuming. What's going to be a lot more efficient for us is using online calculators to calculate R. So we're going to go back and look at the examples that we had from McDonald's salads and the stat sprinters, and we're going to calculate the correlation coefficients and try and interpret them. Okay? Because we had two pretty different types of relationships there, and I want you to see how the correlation coefficient aligns with what we did previously. Alright, so we're going back to our sprint time and long jump distance example from the last lecture, and you'll see that I've got also my Canvas homepage open, and I want to click on calculators to find where we can utilize a two variable statistics calculator. So if you scroll down, we are now into Unit 2, and here's a two variable statistics calculator. Clicking on this link will take me to this page, and what I want to do is go ahead and click data, and I want to type in my own data. So we can go ahead and type in column A and column B are X and Y variables. You just want to make sure that they match. So my first individual had a sprint time of 5.41 seconds and jumped 171 inches. Go ahead and type in along with me these remaining values. Alright, so I've got my data all plugged in. Now what I should be able to do is just go ahead and click on the Statistics tab over here, and that's going to give you some information. Now we get the mean and standard deviation for each one of our two variables. So the average sprint time was 6.3 seconds, the average long jump distance was 124.5 inches, and then we have our standard deviation as well. Now we get this thing called the regression line, which we'll get into later, but what we really want to focus on for right now is this one here, correlation R equals negative 0.8380. Try to remember that number, negative 0.8380. If we click scatter plot now, you will see that you can make yourself a scatter plot using this online calculator. The scale is a little bit weird, you'll see, and it doesn't actually title the X and Y by their variable names because we didn't type them in. But you do see that it's the exact same kind of relationship and orientation as we saw on mine that I drew a few days ago. Okay? But let's go back to this number and try to remember it. Our correlation coefficient is negative 0.8380. And we want to make sure as soon as we see that we have a linear relationship, then this is a valid calculation and we can utilize it. So let's try and go back and try to interpret this number in just a little bit. So coming back now to today's notes, we can see that, or we can write this out, that we had our stats sprinters had a correlation coefficient of negative 0.8380. Okay, now what we can see from this is that there is a negative relationship, and if we think back to what our note said, I believe we said this was a strong relationship between the two, or maybe it was moderately strong. So with this, I can still utilize that same kind of interpretation, and I'm going to write this out and we'll try and make some connections in just a little bit. So there is a strong negative linear relationship between sprinters or sprint time and long jump distance. That's interpreting the correlation coefficient in context. So it's the exact same thing that we did basically when we were looking at the scatter plot itself. Now, what I want you guys to do is take a look at the McDonald's salads and try to do that on your own. Alright, so hopefully you were able to utilize that calculator on your own using the previous McDonald's fat and sodium content in their salads, that data set, and you should have found that your correlation coefficient was 0.8927. And I'm telling you that this means that there is a strong positive relationship between fat and sodium content in McDonald's salads. Now you might notice that we used a little bit of wishy-washy language in the previous lecture, talking about moderate strength here, or maybe it's moderate to moderately strong and we're not really sure. Again, this is where we can find that our eyes will tend to deceive us, and we actually want to see a numerical way to describe strength and direction in quantitative data. Okay? Now, the way we do that is with this correlation coefficient, and these two correlation coefficients are actually representing very, very strong relationships. Let's see why by defining a few facts about the correlation coefficient. So some of the facts about R. First off, R is only going to take a value between -1 and +1. It can go all the way up to -1 and +1, but you'll never have a correlation coefficient of 1.25. You'll never have a correlation of 1.01. You'll never have a correlation of 10 or 5 or 9,000. It's never going to happen. It's always between -1 and 1. Moreover, we are going to tell you that the correlation coefficient does not imply causation. Okay, this is one of the huge ideas about correlation. The correlation is not the same as causation. Correlation just says that two variables are associated with each other. They're coincidental. They happen at the same time. If we have something with fat, high fat, it might have high sodium as well. Okay, those are going to be correlated. It doesn't say that fat causes sodium. Those two things can be independent, but they might just happen at the same time. Okay, so never say cause and effect when we are talking about correlation. Just say they're correlated, associated, or they are related to each other. That's what you want to do. Next, strength. How do we actually quantify this? Well, when we talk about strength, if we have a number for the correlation coefficient that is close to 1 or -1, then that is going to be strong. The closer you are to either 1 or -1 tells you that you have a strong relationship. The closer you are to 0 tells you you have a weak relationship. It'll seem like complete random scatter if we have a correlation of 0. Now, if you have something that is exactly positive or -1, we would say that is a perfect association, which almost never happens unless you're actually in an algebra course and you're looking at some kind of line. All the dots in a data set would lie exactly on that line, and that would be a perfect correlation. Okay? Now, since correlation can take either positive or negative values, this should be pretty obvious. Direction is positive if the sign is positive. Okay, if R is a positive 0.8927 like we saw in the last example, then it's a positive association. If the correlation coefficient is negative, then we have a negative association between our two variables. So that should make sense. Last thing that we want to make sure we address, R is dimensionless. It has no units. You'll notice that I didn't talk about seconds or inches when I was talking about the stats sprinters correlation coefficient. I didn't write down milligrams or grams of sodium or fat when I was talking about the McDonald's salads. Okay, this is a dimensionless unit because we know we might be talking about two completely different units of measurement. Okay, so there are no units of measurement. They do not exist for the correlation coefficient. They essentially cancel each other out. And that should make sense because we remember that this is the product of z-scores. And z-scores have no dimension. They have no units. Same thing with the correlation coefficient. Now, let's try and get a little bit more in detail about how we can describe strength. The rule of thumb for correlation coefficient, there's no hard and fast rule, but here's what I describe. Here's what I talk about. Okay, I know that I'm going to be somewhere between -1 and +1. So I'm going to make a number line here for my correlation coefficient. Right smack in the middle is going to be 0. Now, I might have maybe between, like, say, -0.3 and +0.3. And anything that's within here, I'm going to say that's going to be considered weak. Anything that's going to maybe be between 0.5 and, say, like 0.7, whether it's positive or negative. Let's go ahead and do that in blue. I'm going to call this like the moderate range. And you're going to be able to start to see, like, okay, well, if something maybe has a correlation of 0.6, it's not super strong, but it's not really weak either. So I would call that moderately strong. And since it's on the positive side, I would say that's maybe moderately strong and positive, right? That's how I would interpret that correlation. If it was -0.4 down over here, that might be something I would say that's closer to the weak end of the scale. So that's moderately weak and negative. And that's how you can start to use that wishy-washy language, use that moderate term to bridge the gap between something that's weak or something that's strong. Okay? Anything that's really, really close to 0, though, we would say it's essentially no association at all. And then anything that's going to be 0.7 or above, or -0.7 or below, those we would say are going to be strong associations. So strong to very strong will be anything in here, in these ranges. Okay? Let's try to put that into practice using this number line and using some examples. Let's go ahead and approximate these correlation coefficients. This first one, a lot of students will start saying, oh, okay, well, that's pretty obviously negative. Is it? I don't know. I feel like I could draw a line that's going up and to the right that shows that it's positive and get kind of the same picture, really. So this one, the more random scatter I see, the more it looks just completely random, the more I would say it has no association. So I would say something that's going to have no association, maybe I'm going to call it 0, or this could be maybe -0.1 or +0.1, something like that. Okay, here, the next one, it looks like we're pretty close. Like it's pretty obvious now we can see there's a negative direction. But those dots are still really pretty far away from each other. So this is still kind of weak, but at least it does show somewhat of a linear relationship that's pretty clearly negative. I would maybe put that at -0.3 or -0.4 or something like that. Here, it looks like since I've got these dots up here that are a little bit closer to the line, I would say this would be maybe closer to 0.5, okay? Showing a moderate relationship. It's a little bit stronger than the previous one. The next one here, I would say this one looks still a little bit stronger. Maybe this would be getting closer to 0.6, right? The dots are a little bit closer to the line. So maybe we would say this is going to be a -0.6. Next one here, we're getting a lot closer to the line. This is going to be very, very strong. I would say this is probably going to be closer to like 0.8, 0.9, something like that. So maybe we would call this one, I don't know, 0.8, 0.85. Again, without any scale, it's tough to tell. It's still hard to eyeball. But what we want to really start to see is like, hey, how are they related to each other? What's a stronger relationship and what's a weaker relationship? That's what I want you to focus on with this example. And then finally, this last one here, it's obviously negative. Those dots are extremely close to each other, but they're not exactly on the line. So I'm going to put this one as, this is about as strong as we're going to see without actually getting one. So maybe this would be like ours, -0.99. Okay. The biggest thing I can suggest to you is, don't trust your eyeballs as much as you can trust that calculator. But do remember that your calculator for the correlation coefficient is only going to be something that is applicable if we know that there's a linear relationship. So, big note for you, always look at your scatter plot before interpreting your correlation coefficient. You have to make sure that your scatter plot is showing a linear relationship. Otherwise, R is meaningless. If you have a curve, then R doesn't matter. This is something that only really works for relationships that are linear. All right. Thank you guys so much for watching. Have a wonderful day, and I will see you next time.